Hi everyone. I'm Peter Saxton. I'm crowd hailer on the internet, if you want to find me, and I work at Pay with Curl, a mobile payments company. This is my go slower pebble. Makes me be calm. If I'm talking too quickly, throw stuff at me. It does happen occasionally. It's not on purpose. So I want to talk about the actor model. Now I believe we've all seen an intro to this, so there's some groundwork which it's going to be more unnecessary, but we're going to do it anyway. So actors. Quickly, they are universal primitive of concurrent computation. They communicate via asynchronous message passing, and they react to messages by making local decisions. And this was first proposed by Carl Hewitt in 1973, who also did this morning's keynote. Here is a quick overview of an actor system. So an actor is a unit of processing, and it's just a sort of a complete entity. There's no more structure below that. And each actor has a mailbox, which is where other actors in the system leave messages, because an important feature is that sending a message to an actor shouldn't depend in any way on what the actor you're sending it to is doing at the time. So there needs to be that separation. So what does it mean for them to be a universal primitive? So, well, everything is an actor. And as an actor, you can do it's about three things. So actors encompass processing, storage, and communication. Asynchronous message passing, what that means sort of in reality is there's no guarantees. So the message you send to an actor is not guaranteed to be received, and the order that you send them is not guaranteed to be the order they're received in. So I've made a little note to myself here that this is actually quite similar to some of the early descriptions of object-oriented programming, which talk about sending a message to an object. In short, the only difference is the asynchronous part. So when you send a message to an object in OOP, the return value is relevant, and when the function call is returned, the object has been updated. This changes that. And so local decisions. So local decisions is another important part of the model. So there's no shared and global state. And everything that the actor does, it does locally first. So what an actor can do is it can create more actors, it can send more messages, and it can change its behavior. So that's what the last one says in longer words. An important part about sending messages is you have to know an address to send a message to it. So addresses should be given to you. So so by local decisions, you don't get to imagine a new actor and send it a message. Like, you have to have been told about it previously. Okay, and in the wild, so actor implementations exist. The most well-known ones are sort of Erlang, which has then got Elixir on top, and then there's Akka in Scala, and there's a few others. I think Rust is pushing one at the moment. But these are the main ones. And so I thought we should start by building our own. And to make this approachable, I was like, let's go JavaScript. JavaScript is a good place to build an actor model. So we're going to run through that. We're going to do everything you need for an actor model in JavaScript. Shouldn't be too hard. So here is our simple actor. Can everyone see this? I hope so. I have no way to fix it. So this encompasses everything we need. So we have a state, which is accessible only in this function. We await for a message. So we have this mailbox, which when we receive, returns a promise. Await is a JavaScript construct which will stop execution until that promise is resolved. We do something, so here we update a counter with our state, and this goes forever. In reality, you might want special messages that stop the actor, stuff like that, but this encapsulates everything we need. And the important thing is somewhere else, something we'll call deliver. So we will deliver a message into our mailbox. So this is our actor. Any questions? I see some friendly faces. Okay, next one. This is the most complicated JavaScript side. So this is everything that will make a blocking mailbox. So the mailbox basically needs a couple of characteristics. One, there needs to be a receive function. And that receive function should return when there's a message. So here we say, so our receive function is going to return a promise, which we will await on. And if there's already a message in our list of messages, we take it off and resolve immediately. And if there is not a message, like our mailbox is currently empty, we set the resolve function to the promise to be left as awaiting, and we return the promise. And the flip side of this is the deliver function. So when we deliver a message, we push the message onto the list of all the messages. And if we already had a receive call made, that means our awaiting will be defined. So we call that function and we say we get rid of it. And this is our mailbox. All right, so let's make our actor a little bit more useful. So we want to separate the what makes an actor from like its behavior. So here we have an init and a handle function. These terms might be familiar from people from other languages, but init is what we do when we start an actor. So we want to return the initial state. And handle, for every message, we take the state and we return the new state. And then inside the actor, so our actor now uses these. So where previously we were explicitly being a counter, we're calling handle and we're calling init at the beginning. OK. So starting our actor. So it's important when you have an actor that we can have more than one actor. So to do this, we have a function here. So this function starts a new actor. And each actor needs a mailbox. Inside the actor, we then need a process. So this is the thing that runs forever. So this run function, just to sort of point out the brackets, this run function is asynchronous, so it returns a promise automatically. This asynchronous function never returns, so this promise never resolves. So this run function lasts forever. Again, in a real implementation, you'd probably want a hook to cancel and shut them off, but this works for our purposes at the moment. The important thing here is that the mailbox that we're using is created inside this function. And we return, so this is essentially a facade at the bottom. So we return the ability to deliver to this mailbox, but we don't return a reference to the mailbox. So it's guaranteed that only this actor can pull messages out of its mailbox. So we've now got a nicely encapsulated actor. OK, so now we can start multiple actors. We just need some way for them to live. So at the moment, I've skipped over a couple of things. The first one is allocating addresses. You need to know where your actors are. The second thing is delivering messages. So you need to route them from one actor to another. And the third one is scheduling, so like making them run. So this sounds like a reasonable challenge, but actually, again, a version 1 is possible with this much code. So what we have here is we have an actor system. We've got a list of actors, starting with none. When we start an actor, we call that original actor function, which will spawn a new actor with init and handle. We put it in the list, and we return an ID. So this start function returns just the position that actor is in the list, so it's just its address. So this is the most simple addressing scheme you can have. Like we have actor 1, and then we have actor 2, and we go on. The other thing we need is to be able to route a message to a given actor for an address. So now we have deliver. So deliver pulls out the appropriate actor out of the list of all the actors and puts the message into the mailbox. I quite like separating. So I've used deliver and dispatch here. It's often talked about sending a message, but because sending a message is a process that takes time, there's actually 3 steps. There's when you when you send the message out from where it's coming from. There's when the message arrives in the mailbox, and then there's when the message is received by the processing actor. And they all have to happen in order, but it can fall over at any point. And then to start this off, so we just return our actor system, which is a function of start and a function of deliver. And this works. You can write actor code in JavaScript doing this. So let's review this trivial actor system. It's concurrent, not parallel. It's cooperative, not preemptive. And it's voluntary, not obligatory. So we'll go through this. So concurrent versus parallel has been mentioned a few times. So something being concurrent is a property of the program, and something being parallel is a property of the implementation. So you obviously can't have a parallel program on a single core machine. But the idea of writing a concurrent program is that you can transparently parallelize it later. This diagram just sort of explains the difference. Like at the top, we have 2 queues, so we can put things in different orders. But there's only one coffee machine, so only one coffee is made at a time. Doesn't matter how you structure queuing up. At the bottom, we have 2 coffee machines, and so we're genuinely making coffee in parallel. So cooperative versus preemptive. So what I mean here is, so in cooperative, this is probably most easily explained by the example. Imagine we write this in our handle function. This is a while loop that runs forever. The actor system we created will freeze. That takes up everything. There's nothing else that can be done, and there's no way to protect against this. Preemptive is when a process can be stopped at any time. So in a preemptive system, writing this code is not a problem because it will run. This actor will never do anything useful again, but it will be periodically unscheduled, and the next one will get to process. This is how programs in operating systems are done. And the final one was voluntary versus mandatory. This is a comparison I haven't seen in other places, but I needed some way to sort of wrap this up. By voluntary, I mean because we're doing this in JavaScript, you can opt out at any point. So this is probably why, as much as you can actually write some fairly nice code like this, you're entirely reliant on people behaving for it to work. So for example, the first one, we have an actor system, and we can send a message, which is the empty list, to the actor. And then some point later, we can mutate that, because it's a mutable reference. And so that messes up our guarantees that the only thing that can be shared, that messages are the only thing that causes a change in the system. In the second one, again, we wait for a message, but then we read something from the global state. Like there's nothing in JavaScript that prevents you just calling window. So these are just things that are a limitation of the language we've chosen. And then here's an example of using it. So this is a ping pong program. So what we have here is we have an actor which, so when there's no state, so it behaves the same all the time. So the init function just returns null. If it gets a message of type ping, it sends, so this bit of syntax here is destructuring an object that comes in. So if we get a message with a type and an address, if the type is ping, it sends a message pong back to that same address. So this actor doesn't know about the pinger until it receives that message. But once it receives that message containing address, it is then able to use that address to send the message back. So that's a ping pong program. And so once we've got that set up, we start two actors. And we send a message to A1 saying ping, and we've said it that it come from message 2, and that'll work. So that's now our actor system in JavaScript. OK, so why do all this? So this is an interesting model, but so far it's not much more than a curiosity. So where is shared memory? This is I took this slide from someone else. And basically, so if we have two lots of processing, one of the other models you can have is shared memory. So if we're doing some processing in Sweden and some in Australia, where does the shared memory live? I mean, there is no Venn diagram which is in both. So that's a bust to begin with. Your distributed system. So your system is quite possibly already distributed. You may not be having data centers in Sweden and Australia, but do you have a server and clients? You have more than one machine. Do you have backups or failovers? Then you've got more than one instance of the database running. And even if you get to multi-core, there's processing happening in more than one place. And sending data always has latency and is always unreliable. So the real world works by asynchronous message passing. So the value of this is it's a helpful model. Programming is parallel. So this is the data that goes up to this year. All of these are interesting, but the critical one is the black dots. So the black dots are a trend of the number of logical cores on a microprocessor over the last 42 years. This is a log scale, so this is 1. So each chip had one core from the 70s all the way through to the 2000s. And then in about 2005, that stopped being true. And by this trend graph, we're already getting to 10 to the 2, so 100 cores by 2020. So it's part of the world we now work in. And this is Amdahl's law, which says that, so Amdahl's law says that a program consists of parts that can be parallelized and parts that cannot. The larger amount that can be parallelized, the more benefit you get from having a parallel architecture underneath. This endpoint here being, if your code is entirely sequential, i.e. it has to be run in order, a second core is of no value to you whatsoever. And if we're already talking about 100 core processors, then we want to be going at like 90 to 95% parallel programs. So this was the point about concurrency enabling parallel processing. If you already have a concurrent program, you can use the extra cores just as they come along. So this is a quote from Tony Hoare. So my first message is that concurrency is best regarded as a programming structuring principle. So again, this is just saying concurrency is part of the program, not the implementation. And here's a longer quote from Joe Armstrong, which says, I don't need to read the whole thing out. You can read it while it's up there. But basically, you want to make your units of concurrency as small as possible because they're easy to spread around. If you have, say, just 3 things running concurrently, then obviously you can't use a 4th core. Because if you have hundreds of little actors, they're easy to schedule. They're easy to work with. So this is our actor system 2. I wanted to put this up because I started researching this. So actor system 2, inside the browser, there is the ability to find out the number of cores that the browser has available. And you can start worker processes. So you could make a multi-core schedule if you wanted to. And it's left as an exercise for the reader. Another benefit is communication is abstracted. So this, I was about to explain, this is an envelope. Should be good with that. This one's particularly useful because, as an example, because we have a return address. So this is essentially a ping pong. Miss Joan Johnson might not know about Jane Doe until this arrives. So this envelope contains the information of a new address, which can then be used for a reply. And this hides all the complexity in the middle. So this is a sorting office. You can't see it from a picture, but this is a sorting office on a train. So they used to process the mail on the move. So that's a lot of complexity that you obviously can't specify on an envelope. Cool. And there's also another important thing is the many-to-many relationship. Like if you're sending a message to an address, it can point to many actors, so many actors can work behind one address, like a load balancer as an example there, and one actor can have many addresses. So you can use Google or you can use its IP. So one final advantage of the actor model, which I don't think is talked about enough, is you now have only one side effect. Side effects are tricky to deal with. And you can model everything as a message. So if you want to know the time, you send a message to the clock process. Sometimes this is more trouble than it's worth. Pretty much every implementation treads a line between where this is useful and where this isn't useful. For example, in Erlang, you can call random number and you can call clock just in code. You don't call out. But if you so wished, you can model everything as an explicit message. And I wanted to mention this because there are certain areas of research, and there was a talk earlier today which I hope might talk more about this, but there's these things called session types, and they're essentially a type specification for units of computation and the messages they send between them. So using these, and they are very hard to use, there is the promise, I have no idea how it works in practice or how far we can go down this path, of the compiler checking your program for race conditions and deadlocks, which is an intriguing possibility because it's a long way from true in what I currently work on. Okay. So we've talked about the actor model. It's useful for concurrent programming. Let's build a server. So HTTP is message passing. It even says so in the spec. It's the phrase that they use. So this is from the HTTP spec. And it says they use self-descriptive message payloads. So the message contains everything it needs, including the address of where to send it and all the content you might process. We aren't going to use our JavaScript model anymore. That was a fun intro, but if you're going to do anything like this, we don't really want to accidentally opt out of these guarantees. So here's another quote for Erlang. So the Erlang view of the world is that everything is a process, and processes can interact only by exchanging messages. This is valuable because you don't have to watch yourself to do the right thing. What is not said here is those messages are always immutable, and there's no global state. I mean, you can kind of pretend on the global state point of view with name processes, but messages will always be immutable. So Raxx. So Raxx is what I've been working on recently. It's just an Elixir web interface. Out of interest, who here has worked with Elixir or Erlang? Okay, so I think I've picked up that crowd. Okay, so Raxx is the interface, which is just copied from other languages or evolved from other languages, and ACE is a server which runs that. So taking our lessons from we want lots of small processes, I'm just like paraphrasing Joe at this point, but we do move on. So yeah, we don't have one web server managing 2 million sessions. We have 2 million web servers. So when you make an HTTP request, you don't need to know that anyone else is making a request. So you might as well be talking to a server on your own. So the simplest way to model this is to have your own server. So this is how ACE is set up. And this is not some code. This is a diagram. But it's a very close representation of what actually goes on inside the server. So the blue processors on the right, they're all individual PIDs. And they act as a server for just one connection. They're all supervised. So if they die, they're under the server supervisor. We don't touch much on sort of fault handling in this talk, but that's a nice way to group them. And then we have this governor process. So the governor process is responsible for starting a server process. So at this point, we have 2 connected users, and we have 1 process waiting. So this server is ready for a connection. So someone comes along and makes a connection. This is represented as a message. So the socket, it sends a message to the server process. The server process sends a message to its governor going, I'm now going to do some work. The governor says, start me a new server. A new server is started. So each one is just doing what it's capable of doing locally. And then we end up with this situation. So the server supervisor created that server. When created, it was the only process that knew about it. So it had to send a message back. The message back here says a link. So a link is just a construct in the Erlang environment that says, if the server fails, send me a message. This is just built on top of pinging underneath, like it's still message passing all the way down. This is the interface. So in Erlang, as you all know, so I think as most of you are here, we're quick about this. The concept of a server exists in Erlang. So we don't work with send and receives. We normally work with the handle callback. And the reason for this is it's easy to test. So this is the simplest gen server you could imagine. So when you give it a request, you get a response. Raxx simple server does the same thing. So there's more to it, but this is the state, the request, and you return a data structure representing the response. There's more, so there's helpers. So there's ways of building the headers so you don't have to work with one giant data structure. The request is itself a data structure which pulls out useful information. Here we're just doing pattern matching. So the path is already split up into sections. So what we're doing here is we're matching on any path which begins /name, because that's a string, but then the second one is a variable, so it will match on any string. So /name Brian would match there. And then the state is just whatever we start our server with, so there's an initial state. Here we can have a greeting. So what about streaming? So streaming was an interesting challenge while doing this. For a long time, I thought you might actually have to fall out and do a different model. If any of you are familiar with Plug, they model streaming as a separate thing. But I think it is possible to model streaming as just a series of messages. So if you have a client and a server and you're interested in more fine-grained control, the request is the beginning of the request, lots of bits of body, and then the end of the request. And the same for the response. And you can consider those as messages. The interesting thing now is the server has a prolonged state, so you need to sort of manage the state between these messages. But this is how I think that can be done. So here we have a handle head, which is when the request arrives. So this is called when all the headers for the request have arrived. There's no more fine-grained control than that, so you can't opt out when the first headers arrive. So what we have here is we have an upload server. It's no longer a simple server anymore. So what we do is we don't really care about the state to begin with. We've got a request that's coming to the upload. So we open a file. Our new state is now this file in this device. Every time more data comes in, we write it. And then the final message is this handle tail. We don't care what's in it. So we just respond. So we finally respond at the bottom. These structures in the middle so the return value from all of these is the messages you'd like to send and the new state. So at the beginning, we don't have any messages to send. This is the empty list. In the middle, we don't have anything to send. And at the end, we send the whole response. If you want to, this can be turned around. So for streaming the response, you could send the head of the response here and then send data chunks in the middle. It's worth pointing out that actually this is more than just like an experiment of mine now. I've been working on this for 2 years. We use it in production in some of our services. We do use other stuff as well. But it has all the things you might want. It's far more compositional, so you start with very minimal amounts. So stuff like templates are in separate projects. Code reloading there's this Raxx kit project which gives you a generator if you find those things helpful, but it's very easy to get started without any of those. Just add it to a mixed project. Okay, next. So here's our client server, and we've said we can model them as actors sending messages. But why do we have to start sending a message from the client to the server? Why not send messages from the server to the client? Why not send messages from client to client? So this is where things get far more experimental. It's all about addresses, really. So all we really need is an appropriate way of addressing. So Gen Browser is a proof of concept in this area. It treats clients as just another process. So the aim of this, so the name Gen Browser comes from the Erlang terminology, but there's nothing special about it being sort of Erlang on the back end. The idea is that a client can have an address, and you can just directly send them messages. You don't need to wait for them to send a request. And if you do that, what can you do with it? So now we're back to the JavaScript code. This is how you start Gen Browser in the client. So when you start it, you need to tell it what backend it's using. Like, there needs to be some level of communication. When you start a client, you get an address, which is your address, which any other process in the system can use to send you a message to that specific browser instance. You get a mailbox, which is exactly the same as the simple mailbox I showed earlier, which is where you receive messages. And you have a send function, so you can send messages using the address. And then there's this communal key, which is the one new thing. So the browser, because it's not in a trusted environment, is not allowed to create its own processes. So once it gets an address, it can't spawn new processes. It's certainly not allowed to discover processes on the server that you haven't told it about. So the communal key is just a map of addresses for server process that you give it at startup. So for example, you can make a game server where the communal process includes a process to pair up. So the clients can send a message saying, pair me up with someone. Once 2 messages have been received, it knows how to send a message to both clients going, I've got you a pair, and they can then talk directly from that point onwards. So that's how you start. The other interesting thing with this is that disconnected clients are not unusual. So the system doesn't automatically kill a client if it can't talk to them anymore. At the moment, it's up to the application to decide how often it should hear back from a client to consider it still alive. So here's how you'd send messages from a server to a client. So here's G2GCZA was the address we got earlier. And we want to send a message ping. And this message ping has an address to the, so self is the process ID for the server process that we're on. And if we do this, and we send this to the client, and the client's set up to send a pong, we'll get a direct message back to our server process. To send a message from a different client, to our first client, we end up with exactly the same constructs. So we can again use that string address. We can send a message of type ping. So maybe I should have been clear, yeah, it was Elixir code before. It's now JavaScript code. So the code, although looking different, is the same code. We have a send, where you send your own address, and then you wait for a reply, which you receive from a mailbox. So it's exactly the same code if you squint. So at this point, so a couple of things which you need to make this work. There should only be one actor per mailbox. So a couple of the things Gen Browser does is to basically make sure these guarantees are not violated. So the first one is this actor per mailbox. So when a client connects, it's given an ID, a cursor, and that is signed by the server. So no other client can forge that because the client never sends it anywhere. That never leaves the browser. So when the browser reconnects, it reconnects with that cursor, and it gets access to the same mailbox, but it never shares that cursor anywhere else. So it's always the same one. And actually, it doesn't even get into the JavaScript code. It's entirely within the browser helper for event source processing. The other thing is that addresses need to be unforgeable. So again, the client, so if we start from this the other way around, who knows of the object capability model? No one at all. So I think it comes from the capabilities that were talked about in the keynote this morning. So the capability model is basically you have keys for permissions for what you can do. So, if someone's locked a shed and you give them the key, they can unlock the shed. But the important thing is if they give the key to someone else, the person they give it to can also unlock the shed. So capabilities are transferable, and essentially in this model, the capability is the address. So once you know an address of someone, you can send them messages. That's the whole security model. But you shouldn't be able to fabricate someone's address before they give it to you or it's passed to you. So again, the same way this is done is used by signing. Okay. So one more thing I want to say about, because we have quite an Erlang audience, is so inside Erlang it's possible to name processes. So you can use the via tuple or the global tuple. So the addresses that are sent are actually the appropriate global tuple for the backend process, turned into a binary using Erlang term to binary, and then that binary string is signed, which means you can, on any backend node, check the signature, decode the via tuple, and then send it a call message, a cast message, look up its state, look up its PID, like all of the full, the mirroring PID on the back is now fully available in a normal PID in the system. Obviously on the client, you can't decode it because you can't do anything with the signature. So if you want to try it out, if you're feeling maverick, you can throw it into a plug or a Phoenix application using a just plug middleware here. The one important thing about this is the body needs to already be decoded. So if you're putting in the parsers, the body needs to be decoded first. It assumes that everything is JSON encodable. Maybe it would be nice to have different layers, but for the moment, JSON's native in JavaScript. It was a sensible trade-off. If you don't know Elixir or Erlang, there is a possibility to run it from Docker, so you can start the backend server. That doesn't allow you to add your own backend processes, obviously, but you get started with a name registry process. So from the client, you can start yourself as a browser, get an address, and then you can register it to a certain name. There's no security behind that, so that's just a playground. So what's behind the address? Oh, so I did have this slide. OK, so how long have I got? It's 5 minutes. All right, so as I was saying, the Gen browser references a backend process which is responsible for communication with that particular client. As we talked about, the fact that there's a backend process here is not really important. The whole value of message passing is you can abstract the middle steps. So when you send a request to Google, you don't say, send it to my router, send it to the next node, so on. You send it to the end process. So this works perfectly well as an abstraction, as an address. And it got me thinking, what other things can you actually wrap up as an address? So a browser is just some client device. There's no reason why it has to be a browser. Any client will do. So you can send messages directly to an IoT sensor. You could send messages directly to a persistent actor, so like the equivalent of like a database row. So a persistent actor or a virtual actor is a concept in stuff like Orleans. So again, as long as it looks like there's only one processing and a mailbox is consumed serially, it behaves like an actor. The final one is interesting. An email inbox. That actually works as a mailbox. But at this point, the actor for the mailbox is a human. So humans are the universal primitive of concurrency. They communicate via synchronous message passing, and they have no shared memory. In fact, the only important difference between a human and a computational actor is that a human is non-deterministic. So you don't know which answer they're going to give you beforehand. However, it's possible to constrain. So for example, if you send someone an email with 2 links, which have signed addresses saying click Pong, for example, or one link, for example, the human can choose to click that link or not click that link. If they don't click that link, you get a timeout. If they do click that link, they're still receiving emails. So you can loop them in to quite a lot of the description. So that's me. There's an interesting discussion around how crazy I am here. I don't even know if it's useful. I don't know if it's horribly demoralizing to view our users of the system in this way, or if it might be very insightful. Here's the code. You can have a play with it. I'm Twitter I'm CrowdHailer on Twitter. So questions, comments, criticisms, all welcome. Cheers.
Any questions? Anyone?
Thanks for your talk. So I just wanted to ask, how far have you gone with regards to the second generation actor system with preemptive multitasking in JavaScript?
So not very far at all. The reason being that I think there are two things which need to be done next, because this, I mean, it's definitely experimental. The first thing is this a useful model? So what I would like to spend my time on is the session typing. Like if I type a session of sending an email to a user and that user logging in or not logging in, for example, if that gives me a useful description about my system, then it's worth putting the effort in. If that turns out to be a massive overhead, then it's not worth putting the effort in. But I don't think many pieces are necessary, particularly if you're happy with the voluntary model, that you're relying on the application developer to be well behaved. You could probably get a fairly primitive implementation fairly quickly, I reckon.
You mentioned that you have production systems running your project. I'm just wondering how many actors have you have running at the same time in your system? Like, how do you stress this or?
So just to stress, I'm using this one in production and not this one. So I have no idea how many actors we're running in production. It's not an important metric. They're so lightweight, you can start millions without it being a problem. I know our defaults on the server implementation. So the server starts a process. So it has a pool of waiting processes. So in the diagram I showed you, there was just one process waiting. We actually have 100 processes waiting and 100 governors. And then each of those processes has a task queue. So I know merely starting the system, we're on at least 300 processes. And then every single user is going to add 3 to that number. But that's nowhere near the limits. Like, we've done experiments where you can have hundreds of thousands. And it's not something you think about. Like, if you're worried about the number of processes, you're doing something unusual. Oh, so in JavaScript land. Oh, so in JavaScript land, actually, what did I do? I got up to tens of thousands because it's single-threaded, and I don't know how it stores them, but it's not. I don't know how it stores them, but they're just put in a list somewhere, so they don't actually take up that much space. So you can do a round robin to some. I haven't pushed the limits of that because there's no point measuring that for performance, because until you parallelize it, it's all overhead. Like, everything I'm doing is making the life slower by adding an abstraction, which in the future is meant to make it faster, but at the moment it's just slower. So yeah, how performant that actor system in a browser is okay. I am actually now interested. I was about to say I'm not interested. It's important to check it works first, but now you've made me quite curious. I'm going to find out. Yeah.
I can just say it loudly.
No.
So where you had your client connecting to localhost 4000, have you tried to connect, or can the client choose to disconnect from the server? So can it can the client start and then can it subscribe? And then the follow-up to that is, could it subscribe to multiple servers?
It could join multiple
and unsubscribe again if it decides it doesn't want to listen to that.
So
anything on that server.
So unsubscribing is fine. That's implemented. You can just voluntarily deal with that. And also, a client misbehaving and going offline and never coming back is something that has to be dealt with. So as a client, you can just stop doing anything, and eventually the server will go, oh, okay, they're not alive anymore. In terms of subscribing to multiple servers, that's interesting because you would get a different address from each of them. So the server wouldn't know. Well, so you can have a cluster of nodes behind one URL. So you could have a client connect to get an address from the system, and because the system can be distributed, you could send messages to any of those nodes, and it would route through the via tuple appropriately. But connecting to 2 different services, but also you would.
Different services.
So yeah, you would have 2 addresses. Yeah. and you would have two mailboxes. But again, this is the thing: a single actor can have multiple addresses. Like that is part of the model. So, and I guess it's important that you wouldn't I can't if you connect to like bbc.co.uk and google.com, they obviously can't agree to give you the same address. There's no coordination between two servers if they're utterly separated.
No, but if both those two send me emails, I'll get them into my email
Yeah.
client, and then I can choose to unsubscribe from there.
Yeah, so the those strings that I showed you, you did have to know which system you were talking to. So the address, so if you subscribe to localhost 8080 and get an address, and then you subscribe to localhost 4000 and get a different address, if you send anything to, so there's a HTTP endpoint where you send messages to, like send/address/message. If you were to try to use that send endpoint on the localhost 4000 with the 8080 address, it wouldn't know about it, and it would just be like, I don't know that address. It would assume you've either forged it or done something weird, and it also wouldn't have the same signing secret, so it just wouldn't decode it. It would just fall to pieces. But as long as you keep track of where they've come from, you could do that. It probably makes most sense to consider it as like a background, and you want this to be a orchestration layer, so everything you're thinking about is using the same one, and you could have. If you wanted a microservice architecture, they could all subscribe and get their own addresses and forward it through that system. But yeah, two actor systems at the same time is confusing, I would say. Yeah.